What are some different ways in which these earliest life forms made their livings? I mean, we're most familiar with creatures that eat and breathe, and then others that make energy out of sunlight. But what are some of the other options? I saw that there were iron breathing bacteria at some point. Uh,
There still are. They're probably in
oh,
your
huh.
house. Yeah. Again, that's why it pays to pay attention to the ways that bacteria make a living because, you know, animals respire aerobically, which they can only do because they have mitochondria, which used to be bacteria. Plants photosynthesize, which they can only do because they have originally symbiotic cyanobacteria for photosynthesis. But when you get into bacteria, many of them can respire in the absence of oxygen because they can use other oxidants, things like sulfate, uh, oxidized iron, some nitrate, uh, as oxidants for respiration. There are 6 or 7 different kinds of photosynthesis that don't use water as a source of electrons and don't generate oxygen. There are metabolisms that only bacteria and their cousins, the archaea, can do, like chemosynthesis, that is something like photosynthesis, in which you fix CO2 into organic matter, but the energy comes from chemical reactions rather than sunlight. And so if you look back at those, again, I think there's considerable uncertainty about what early metabolisms were, but there are at least many people who believe that they did involve very early on carbon fixation via a process that's now only found in some microbes, and probably were chemosynthetic. That is, they took advantage of chemical gradients on the early Earth and used that to drive the fixation of carbon. Now, in some ways, the key um, metabolism to evolve was so-called oxygenic photosynthesis, which we always think of as green plant photosynthesis, although we really ought to think about it as cyanobacterial photosynthesis because they're the only group of organisms ever to evolve it de novo. And in that one, um, water supplies the electrons needed to reduce CO2 to organic molecules, and oxygen is given off as a byproduct. And that, without that evolutionary event, we would never have come to have an oxygen-rich planet. So it's just maybe the primary example of Earth's physical environment having a strong dependence on the activities of organisms.
I'm not sure if the nominalization of something that undergoes chemosynthesis is a chemosynthesizer or a chemosynthete. I prefer chemosynthete, I think, for just aesthetic purposes, but I'd like to talk about them for a minute. Do we have reason to believe that there were extremophiles already early in Earth's history? I was actually pleasantly surprised to see that a Stanford researcher once proposed that places like super hot deep sea vents may have been among the only places on Earth to survive at times in Earth's early history, such as when it was being bombarded by meteors.
Yeah, I think it's reasonable to think that on a relatively short time scale, which on the time scale we're talking about could be tens of millions of years, if not hundreds of millions of years, life figured out how to exploit almost every habitable environment. Now, not every environment is habitable. It can be too hot, it can be too dry, it can have too large concentrations of salts, you name it. But there are organisms, as you mentioned, that are called extremophiles because they live, frankly, in environments that we can't. And some of those on the deep sea, where pressures are high, live at temperatures above 100 degrees
113.
Celsius. Yeah, something like that. There are ones that live in very salty in environments. And so all that is a matter of, natural selection, for membranes that can sustain activity under these conditions. There's a lot of things that go on, but I think the evidence, at least from the world we see today, is that life has been very versatile in its ability to evolve, uh, forms that can be sustained in what for us are unusual environments. And again, if you turn all that around, what it really says is that humans and animals in general are actually not very good at exploiting extreme environments, whereas bacteria have done it for billions of years.
Mm-hmm. Yeah, we to leave our equatorial home regions, the only things we really picked up were new clothes and air conditioning, and that hasn't gotten us that far. Unlike tardigrades, which my understanding is they can persist pretty much everywhere, and they don't need new clothes or air conditioning for it. But
yeah, but I'd rather be a human.
Me too.
To be
Me
honest.
too. You already referenced comparative biology, which I expect will fit in here, but when you examine a microfossil, are you able to tell whether it's photosynthetic or carnivorous or anything else about what it did? Because you can't observe it the way that we might a living creature in a lab or a cat in your lap. And as far as my understanding of fossils goes, the creature's original constituents, at least for macroscopic creatures, are gradually replaced by minerals and other deposits. So you're not necessarily even working with the original material. So is there just a close enough resemblance to living creatures that you're able to generate credible hypotheses about how they functioned?
Yeah, largely what we have in the geologic record is morphology, whether that's, a human bone or a clamshell or a trilobite, you name it. And, for those things that are fairly closely related to the living biota, you can say a great deal about them. So if you give me a clamshell that's 100 million years old, I can probably tell you a lot about it because I can compare it to living things that are similar and make some quite reasonable deductions. It gets harder as you go back, deeper in time to things that don't have close living relatives, and gets at its hardest in that, 85% of Earth history that's mostly microbial. But even there, one of the great things about cyanobacteria is that not only are they probably the most important group of organisms ever to evolve because they're responsible for our oxygen-rich atmosphere, but they're different from many kinds of bacteria in they're commonly larger, they commonly have more complicated morphologies and division cycles, and we know a lot about how they decay, how they preserve. So there are things that I can show you that are 2 billion years old that I have very strong confidence that they were cyanobacteria that worked, at least in a broad way, like cyanobacteria do today. And then when we start getting eukaryotic life, one thing that one of my former students, Susanna Porter, found deep within the Grand Canyon in some 740 million year old rocks are about 100 micron things, sort of look like a flask that's open at one end. And we know that those are very similar to groups of protozoans today that actually eat other protozoans. And in fact, Susanna has found evidence of, probably calling it a bite mark isn't the best thing, but of punctures made by predators on these shells. So sometimes you look at it and you can't say much at all, but in other cases, there is a distinct enough morphology, and sometimes you have evidence of behavior through orientation and things like this that we can use. And they tell us a lot. And then finally, there are some examples where we have molecular evidence. Recently, there was a very nice paper on these so-called Ediacaran macrofossils, which most people think, I think correctly, are early animals that are quite distinct from most animals living today. And it was found that they have the remnants of cholesterol in them, which is an animal-specific sterol or steroid molecule. And so even under favorable circumstances, you can even get some molecular preservation that helps zero in on the nature of an organism.